Good afternoon, everyone. So welcome to the colloquium today. And today we get a great pleasure to invite Chia-Jung from Chalmers University in Sweden. And Chia-Jung was an undergrad and a master student at the NTU. And later he became this software engineer, actually working in the ALMA CASA project for 2 years at the ASIAA. And now he moved to the Sweden to study his PhD. And Chia-Jung soon will get his PhD. And his research is with Johnson Tan and on some very interesting question of the star formation. So today he will be talking about from cloud to the dense core. And let's welcome to Chia-Jung. And I leave the stage to Chia-Jung. Please go ahead. Thank you.
So thank you for the introduction. So first, I would like to thank Ken who invited me to have the chance to give the talk. And also, I have to say sorry that I got COVID last week. So if I cough frequently during the presentation, sorry for that. And as you can see, my topic is from clouds to dense cores, and in the background, it shows the simulation of cloud-cloud collision. And then it forms the dense structure, filament, and Prestellar core in the collision of clouds. But why are we interested in this topic? So we should start from the massive star formation. I will first give an introduction of massive star formation, and then back to the cloud collisions about the core mass function and the core properties. Then I will move to the chemistry in these star forming regions, includes the CO depletion and also the Deuterium fractionation. Then I will give the summary. So first, why are we interested in massive stars? Because it's very powerful and have a strong feedback to the universe, help to show universe includes the radiation, stellar wind, supernova when they die, and also enrich the environment with their habitat elements. However, it's very hard to study massive star formation because they usually stay in an environment with high extinction, and also they are rare, have short lifetime. So all these things make it hard to be studied. But a fact we know is that the massive stars tend to form in cluster. So in generally, we know that the star formation happens in molecular clouds, and the cycle is in the interstellar medium is from the diffuse gas that cool down to molecular clouds and form in cores. Then the cores form protostar and then solar system. However, we are not sure whether the massive stars are exactly from Prestellar cores. So currently, there are two main candidates for the massive star formation theory. One is turbulent core model, and another one is competitive accretion model. So in competitive accretion model, it says that the massive stars gather the gas chaotically in the cloud and to form massive stars. And it's nature to have the initial mass function in this process, and the massive stars can usually stay in the center of cluster. However, the problem is that maybe it cannot reach really high mass stars. And another theory is the turbulent core model. Basically, it's a scale-up low mass star formation theory, and it requires the existence of massive Prestellar cores. These cores are supported by turbulence or magnetic field so that it can collapse orderly to form a massive star. And this allows the isolated massive stars exist. But it also needs the coarse mass function to be similar to initial mass function. So if we would like to study turbulent core model, there are several questions we would like to ask. First, can we find the massive Prestellar cores? And are they exist in clusters? What's the core mass function of the cluster? And for each core, we would like to ask, are these core gravitational bounded? Is it rotate? Does it have disk? And also, is the core supported by magnetic field? To answer these properties of the cores, there are some parameters can help us. We can study the zero parameter, study the rotation energy compared with the gravitational energy, and also the mass to flux ratio. So, but then we would like to know whether we can find massive Prestellar core, and the calculation is the effective way or a promising mechanism to form massive Prestellar cores. And it also can form the star cluster. So this back to the question, how does the coarse mass function look like? And observationally, there are also some signals could be interpreted as calculation, like the SIO emission from SIO emission report in Constantino 2018. So here we use the simulation to study the calculation. We follow the setup in UITAO 2017. The properties of each cloud shows on the top right that the clouds are uniform density. The density is around 83 hydrogen nuclei. Radius is 20 parsec. So each of them around, the mass of each day is around 10 to 5 solar mass. And the clouds are turbulized in the beginning. The Vera parameter is around 6.8. But we don't have the driven turbulence, so this value drops fast after we launch the simulation. And they are also magnetized. There is the 10 microgauss magnetic field in the direction of 60 degrees. In the simulation, it also includes the heating and cooling function from the PDR model. And the visual extinction is according to their density in the cell. So the movie shows the colliding case and the non-colliding case. The colliding case collides in a speed of 10 kilometers per second. And we increase the resolution to around 0.01 parsec so that we can identify the cores in the simulation. But we know that simulation doesn't really give us what we see from telescopes. So we also use CASA to do post-processing to generate the synthetic observations. It's the 1.3 millimeter continuum map. And we assume that the source distance is 5 kiloparsec, similar to a source reported in Chen 2018. And the integration time is 3.54. It's a strange value, but we use this to control the noise level, be consistent with the method we use to find cores. And the bin size is around 1.5 arcsecond. Because the file image is very large, it takes time to post-processing the file image, so we cut that into small pieces and then compose it back to the same size. So with the synthetic observation and simulation, we would like to find the cores from their surface density map, and we use dendrogram to do the core identification. It requires 3 parameters, mean value, mean delta, and mean apex. mean value apparently it says the minimum density we need, and the mean delta is the minimum significance for the signal to be identified as a core, and the mean area is the minimum area of the cores. Currently, we use the values 0.1 gram per square centimeter, 0.025 for mean delta and mean area of 2 pixels. So here just an example of the cores found by the dendrogram. And then here is the numbers of cores found by dendrogram. I list some values from the colliding case at 2 mega-year, 3 mega-year, and 4 mega-year, and also for the non-colliding case at 4 mega-year. We test different dendrogram parameter, and the one with the green border is our fiducial value. The red background shows the results from the synthetic observation. And we can find that after CASA post-processing, the cores reduced 1/3 of them are reduced, or even more. Now we have the core information. So we would like to plot the core mass function. So we use the same method used in Chen 2018, which have 5 beams per decade. And the first row shows the colliding case from 2 mega-year, 3 mega-year to 4 mega-year. And the second row shows the non-colliding case. We can see that the core mass function built very slow in the non-colliding case. And the synthetic observation influence the core mass function is smooth than the core mass function. So from the blue curve, it indicates the core mass function found in the simulation density map. And we found that there is a very flat distribution from from 1 solar mass to 10 or even 100 solar mass. But after we do the synthetic observation, the curves become smoother. This also happens to the case at 4 mega-year and also non-colliding case. And with this data, of course, we would like to compare with observations. We have 3 observational data from Chen 2018, Liu 2018, and O'Neill 2021. We use their raw core mass function data, so what they got from the observations, and compare the probability density with our simulation. And they are plotted in orange, yellow, and green. Basically, they are the same in these panels. So the only difference is the curves from our simulation and synthetic observation. But this is not easy for us to see from the figure. So one thing we can do is to do the parallel fitting. This has been proposed that the core mass function, their tail should follow a power law. And in Salpeter 1955, it proposed the value of power law should close to 1.35. And we fit the power law in 3 ranges, that from 1 solar mass, from 1 solar mass to 2 solar mass, and from 10 solar mass. The figure here shows the example that do the fitting from 10 solar mass. And then we have the fitting results here. First, we noticed that the non-colliding case usually have a steeper slope. For example, from the 10 solar mass, the non-colliding case at 4 mega-year has a slope close to 1 or 1.1, 1.2. But the colliding case report the value around 0.7 or 0.8. And if we compare the slope in these 3 ranges with the observational data, we found that the Liu 2018, it could be similar to the colliding case because they have similar slope in these 3 ranges. And the O'Neill 2020 first, it could be similar to the non-colliding case because they have similar slopes. So here are the comparison of core mass function. And then we would like to check the core properties of each core. So first, we check the virial parameter of each core. The figure here shows the radial velocity and the velocity dispersion and the virial parameter of each core. If we focus on the last row, we found that the virial parameter is usually higher than 1, so that the cores from the colliding case usually appear supervirial. But this includes all the gas along the line of sight. So this may have too many contributions from the ambient gas. We would like to get rid of this influence. So we set up the density threshold of 10 to 5 hydrogen nuclei per centimeter cube. And then we found that of course becomes subvirial after we set the density threshold. And the mean value is close to virial equilibrium. That was the colliding case, and now we would like to check the same thing for the non-colliding case. Again, in the simulation or synthetic observation, we find most cores are supervirial. And after we apply the density threshold, most cores becomes subvirial in this non-colliding case. If we compare with the observational data, Chen 2020 report the virial analysis according to some dense gas tracer, and the result shows that these cores are close to virial equilibrium. So maybe it's close to the colliding case. However, there are few cores in this cluster, so maybe it's a bias, and it's hard for us to say it's exactly colliding case or non-colliding case. And then we check the magnetic field in this simulation. The first, the top figure shows the colliding case, and the bottom figure shows the non-colliding case. And in both figures, the first row shows the magnetic field, and the second row is the mass to flux ratio. We see that the magnetic field is around proportional to the core mass. So this leads to that the mass to flux ratio close to constant in the colliding case and also in both in the non-colliding case. And their values are much higher than 1. So these cores are supercritical, and the magnetic field cannot support the cores avoiding collapse. This agrees with our initial weak magnetic field because it was only 10 microgauss. We don't expect it to stop the core collapse. So here is the analysis in the calculation, and then we will have to go back to the slide of turbulent core model. There's one thing we are interested in this course, that's the chemistry, the abundance inherent from the environment or the evolution of these chemical species. But why are we interested in the astrochemistry? Because the chemical species can influence the heating and cooling rates and regulate the fluid motion. The ion species can interact with the magnetic fields and have the effect of ambipolar diffusion, maybe slow down the collapse. And also the signals from these chemical species can help us interpret the local visible properties, like the cosmic ray ionization rate or the chemical ages. So one thing happens in the cores is that the CO freeze out. We usually use COHCO plus or HCN to track the dense gas. However, in the Prestellar cores, the environment is very dense and cold. The density higher than 10 to 5 hydrogen nuclei per cube centimeter. Temperature is around 15 Kelvin. And in this kind of environment, CO tends to freeze on the dust grain. And here is the example that Hernandez 2012. Here it shows the CO depletion map. And after CO freeze out, another interesting happens, that's the deuterium fractionation. So in interstellar medium, we usually observe that the deuterium versus hydrogen is around 10 to minus 5. But we can see that the fraction of deuterated species could increase in Prestellar core, like H2D plus or N2D plus. The ratio of N2D plus versus N2D, N2H plus could be much higher than 10 to minus 5. And this has been found in many Prestellar core like the L1544. So how this process happens, first that in the Prestellar core is from H3 plus, and the H3 plus can interact with HD, then produce the H2D plus. Because H2D plus is heavier than H3 plus, so it's hard for the reaction to go back to H3 plus. So here is the process that in the Prestellar core is from H3 plus, and then from H2D plus, then H2D plus, or even higher deuterated from E2H plus, E3 plus, they can pass the deuterium to other species, and from DCO plus and 2D plus, etc. However, we found that the H2D plus, we know that H2D plus it can interact with also molecular hydrogen and go back to H3 plus. And also the H3 plus, it could be destroyed by CO or oxygen. So if the environment has high CO abundance or high also molecular hydrogen, then this process could be stopped. So here we know two important factors. One is autopower ratio of molecular hydrogen, and another one is the CO depletion factor. This influences the rate of deuterium fractionation. And to study this chemical process, we would like to couple the astrochemistry with hydrodynamics simulation. So here is the equation describe the evolution of each species. It includes the term of advection, diffusion, and also the construction and destruction, means the chemical reactions. Without later splitting, we separated to hydro parts and chemistry parts. So the hydro part, the diffusion term is small, so we usually ignore it. And then the hydro part left the advection, and then the chemistry part have the construction and the destruction. So this part the advection can be handled by hydrodynamical code, but we need to have another chemical solver to solve the chemical reactions. But one problem to include this chemical reaction to hydrodynamics is the performance. So here, when we include the chemical reactions into the simulation, it usually takes much longer time than the pure hydrodynamic simulation. The figure shows the performance test that we try to couple with different sizes of network with the hydrodynamic code. And we found that the performance or the time consumption is around proportional to the number of reactions. So if we include a chemical network having 3,000 reactions, that's the maximum we have in this example, then the speed is 3,000 times slower. So for a 1 hour hydrodynamics code simulation, it will take 40 days to finish the chemistry. That's unpractical. So a simple way to improve is that we active the chemistry every hydro time step, because if we know that the chemical time scale is much longer than hydro time scale. And we're also trying to improve the performance of chemical solver. So we are developing our tool. It also provides a convenient interface for users to create the chemical network and the chemical solver. So users can create the chemical network in Python and then export it to chemical solver. Then the chemical solver can be wrapped to Python module, and you can code you can keep using Python to code the generated solver. So here are some features. We are focusing on the high performance, convert the chemical network to C++ code, and currently it supports for different solvers from Sundials and Boost library. One of the solver is working on GPU. We are trying to optimize it. And this package can help you create C++ static or shared library, and also Python module, so you can include it to any code easily. And also it supports command line tool. So if you have a text file of chemical network, you can just put the text file there and let it export the chemical solver. Currently, it supports KIDA-UMIS, Chrome, and UCL chem network format. So if you are the user, maybe you can try this new tool. Now, I'm using this to the code I developed to include the chemical network into the calculation simulation. So it follows the same physics, the heating cooling function, the same visual extinction density relationship, and use the same cosmic ray ionization rate. But we include a reduced chemical network from UCL Chem, which includes 87 species and around 1,000 reactions. This reaction has a simple model for depletion and desorption and simple surface reactions. But when we include this chemical network, we cannot achieve the same resolution because it takes too much time. So the resolution is down back to 0.125. The table shows the initial abundance. Initially, carbon are in CO and other species are in atomic form. In the movie, we can see that the CO built up when these two clouds collapse, colliding together. Now, except for CO, of course, we can get the information of other species like HCO plus or HCN, which are even dense gas tracer. So we can see that they form the structure in the simulation. And one interesting we would like to know is the CO depletion factor, because it happens in the Prestellar core and influence the Deuterium fractionation. So we found that there are some bright dots appears in the center in the end of the simulation. If we zoom in to the figure, we see that here are some dots in the simulation, which could shows the CO depletion in Prestellar cores. And we try to compare the results with some observational data we have. We found that in the densest region, it can match with some, the CO depletion factor could match with some data, but the density is much higher. This could be because of the influence of bin size, or maybe we should try use the lower cosmic ray ionization rate. But if except but the results also match with another observational results. So the next thing I would like to talk is the Deuterium fractionation in massive Prestellar core. So I have introduced that the Deuterium fractionation happens in Prestellar cores. And here is the example of massive Prestellar cores reported in Kong et al. 2016. Actually, there are two sources, C1 North and C1 South. And if we zoom into the C1 South region, we can find C1 South A. It's a protostellar core. And another source is C1 South, which is the Prestellar core. And the mass is around 50 solar mass. The radius around 0.02 parsec. And in the paper of 2016, this has been reported that the deuterium fraction of N2D plus and of N2H plus is higher than 0.5. It's a very high value, so we would like to know how what kind of environment can reach this kind of high value. So we set a simulation of isolated Prestellar core based on the turbulent core model. The core mass is around 60 solar mass, radius is around 0.1 parsec. So the free fall time is around 76 kilo-year, fast collapse core. And for simplicity, the core is isothermal. In the beginning, we make it a little bit super real, but it also doesn't have the driven turbulence, so the value also drops fast. And then the magnetic field is slightly supercritical in the beginning, but not. But the mass to flux ratio is not very high, so there is still some support from magnetic field. And we use enzo and chrome to couple the deuterium fractionation network from Kong 2015 into this simulation, which includes 132 species and more than 3,000 reactions. I have to emphasize that this network doesn't have depletion or desorption reactions, so the abundance of C carbon oxygen in gas phase is fixed. And the table shows the initial abundance that all species from atomic form. So what we do is to study the astrochemical parameters, like the also-pair ratio of molecular hydrogen, temperature, cosmic ray ionization rate, depletion factor of nitrogen, and the depletion factor of CO. So that again, we don't have depletion or desorption reactions, so the depletion factor is fixed in the whole simulation. And then we check the result of the defrag N2H plus. We can see that some simulation could reach a very high value, higher than 0.5, higher than 0.5 reported in the observation data. And some of them start from high, higher defrag because they are from lower also power ratio molecular hydrogen or pre-etched model that the chemical species have evolved in a single group for a few times for several mega year, and then start from that state. But except for compare the defrag, we can also compare the abundance of N2H plus and N2D plus. The Mitinan 2012 and the Kong 2016 are the massive cores we are interested in. So if we try to find the model could match with these cores, we will find this red curve is the best model we have. And the parameter of this model is that temperature at 15 Kelvin, cosmic ray ionization rate is 10 to minus 16. The depletion factor of nitrogen is 100, and the depletion factor of CO is 1000. The initial also power ratio of molecular hydrogen is 0.1. With the best model, we can check the we can check the evolution in this course again. And here shows the map of surface density and magnetic field, and also the current density of N2H plus, N2D plus, and its diffract. The critical density here we use for the N2H plus and N2D plus emission is 8 times 10 to 5 hydrogen per cube centimeter. And that was the one we see from the direction perpendicular to the magnetic field. And right now we try to see the results along the magnetic field. So this one may have a larger emission area. So the next thing we would like to know is the kinematics and dynamics in this course. What will we get if we observe the N2D plus emission? Again, this is the edge on and face on movie. And the first row is the surface density map and magnetic field. The second row shows the radial velocity. With the information of radial velocity, one thing we can do is to estimate the velocity gradient. So here shows the first moment map from N2D plus at point A free fall time. And from this first moment map, we can get the velocity gradient. If we think this velocity gradient could represent the angular momentum, then we can use it to estimate the rotational energy. And here is the example, the result observed in Kong et al. 2018, that the C1 cells is around 18 kilometer per second per parsec, and the C1 cells has no clear rotation, but C1 cells is the photosphere core, so it's not the really precise core. But still, the value puts close to the velocity gradient we get from the simulation. And with the velocity gradient, we use it to estimate the rotational energy. Here we get the rotational energy from the mass from the rotational energy pixel by pixel. But the result is similar to the polytropic model. So if you use polytropic model in observation, it's still an effective estimation. And we found the rotation energy usually is only 10% or even lower. It's only 10% of gravitational energy or even lower. So the rotational energy is mainly come from the inflow motion and the initial turbulence. And another thing we would like to do is again the barrier analysis. So we use the N2D plus to get the velocity dispersion, and use the N2D plus velocity dispersion to have the barrier parameter. This is not the same as the one we have in the beginning. In the beginning, we use the O gas. We include O gas to set the initial barrier parameter to 2. But right now, it's the one C from the N2D plus. And it shows different behavior along the x-axis and z axis. So we see different results from edge-on or face-on direction. And from the edge-on direction, we see that the barrier parameter drops down or becomes subbarrier and then close to barrier equilibrium again in the end. So we can see the effect of magnetic field support the cores. But in the direction parallel to the magnetic field, we see the baroparameter just almost monotonely grows up. So we do not see the effect of magnetic field. So here is the summary that first, we perform the highest resolution of the cloud calculation simulation and down to 0.03 parsec, and so that we can find the cores. And we analyze the core mass function from this simulation, found that the colliding case could match with Liu 2018, and the non-colliding case could match with O'Neill 2021. And most of cores appear superrival in the beginning, but if we set density threshold in the colliding case, it get close to virial equilibrium, and the non-colliding case becomes subvirial. And chemistry is important, so we couple the chemical network with MHD-MR simulation. And one case we study is the massive Prestellar core we couple with Deuterium fractionation network, and found that we need high CO depletion factor and high cosmic ionization rates to get the observed Deuterium fractionation level in this fast collapse core. And the emission from N2D plus usually makes the core appear subvirial because of the magnetic field supports. So thank you for your attention.
Thank you very much. And that's any question? The Sonos. Please ask. Please. You're mute. Hello. That's strange.
I'm sorry. It's not. And I was not able to talk from my. So my question is, you it's not an agent. Can you hear me?
Yes. There's some echo.
Oh, okay. So how did you measure that inclination angle of those filaments? Like you need a face on and how do you know the inclination of the and it does
Could you mute?
Sorry, the echo was strong, and I was thinking whether it's the problem of my microphone.
Oh, it's from your microphone.
I'm not sure. Maybe it's from someone's Mac.
Is it okay now?
It's better now.
Yeah, so I was asking that you said that there is a face-on view and edge-on view of your filament. So in observational point of view, how did you measure that face-on and edge-on view for a filament? And do you use any model, or how do you know that inclination angle of those filaments?
We don't know whether it's face-on or edge-on in observation, so we report both face-on and edge-on, and these results can be compared with observation to decide which one can match it better.
Okay, thank you. And another point, you showed that N2D plus velocity width. So do you expect N2D plus velocity width same for whole filamentary structure, or it is different in the along the whole filamentary structure as well as in the particularly dense core part. So do you see the same kind of velocity pattern?
Sorry, I didn't get it well.
So in your talk, you said that you measured the velocity with for the filaments from the whole filaments, right? Or it is along particularly dense core part. It should be different, or it is same.
So we measure the velocity dispersion for the whole core. So that's you can see that maybe I'm not sure whether you mean the filament you mean is the structure showed in the video. But basically we consider all the area from this map. So maybe this one, the H1 looks like filaments, but the face on is look like the whole plane.
Okay, thank you.
Okay, thank you.
I'm sorry. Yeah.
Dylan, please.
I just a naive question. So at the beginning, at the first part of your talk, you show the comparison between the slope of the core mass function between the collision part. Yes, in this table. So I'm just wondering, there are some region with negative slopes. I'm just curious about what caused that, or any explanation for, or whether or not it's expected for such behavior.
Yeah, so here the negative value you see is from this flat region, and yeah, it's very flat, and you can see that the value is also close to zero. So we do not really compare this with the observation because it's totally come from the simulation. And in observation, you can see that it gives you totally different core mass function. I mean, from the synthetic observation.
Oh, sorry. So could you go back to previous the table? To the table, the row listing with the ALMA, that's the observation or the synthetic.
Yeah, this append with ALMA means synthetic observation.
I see. Okay.
Yeah.
Okay. Cool. Thanks.
Thank you.
Thank you.
Any other questions?
So may I ask you the magnetic field in your Calca collision model?
Yeah.
So do you know whether do you know the orientation between the magnetic field and filament in your Calca collision model, and how does it compare with non-colliding model?
Yeah, actually, this is an interesting question that we would like to study in the future.
Okay, thanks.
Okay. Any other questions? So, Jialong, I have a question.
Yeah.
So, you have a very sophisticated chemical reaction network, and including the cooling and the heating. But I was wondering, do you have the dust model?
What do you mean the dust? The dust
Because
formation
most of the
destruction?
interesting chemistry occurs on the surface of the dust.
Yes. So in the case of the CO depletion, let me jump here. So in this one, we have simple surface reactions in model. So that means it includes the reactions happens on grain surface. But of course, this is not the formation of dust grain. We don't have the formation or the destruction of dust grain.
Okay, thank you. Any other questions? Or may I ask another question about the resolutions? And how the resolution in your simulation change your results in the reaction part? Is that very?
In which,
I mean,
which part?
Yeah. Can you converge the results with high resolution study? You mean you increase the resolution? I will expect maybe your result will finally converge.
So you mean the calculation simulation, right?
Mm.
Yeah. So currently we cannot get the resolution higher than this level. So this is the highest resolution we have. But we do test the case with one level lower resolution. And they have similar behavior, but of course the result is not completely the same. And yeah, so there's a summer student is working on this data, and also she will try to study the orientation of magnetic field and the filament.
Okay. Any comments, questions, suggestions? Okay, so if not, then let's finish our colloquy roughly the same time, 5 minutes earlier. So that's thanks Chia-Jung again, and thanks everyone for joining the colloquy today.